Just gonna quickly double check we're live streaming and then we can start. Sounds like we are. All right. So I'm here today to answer your questions, I suppose, about the exam, but I'll take any question. Life, liberty, pursuit of happiness, whatever you got. Who's first? Go.
I was having trouble with the finding the maximum allowable cutting force.
Yeah, so there was a couple different versions of that card. It was one question, but there was a bunch of different numbers associated. So different. What were the pieces of information that are given? You don't need to tell me the numbers, so I'll just take it.
Clamping force.
So a clamping force. And so this clamping force, this is, so when you put the part in the lathe and you step on the foot pedal and the jaws close together, that's what we're talking about there. So we're talking about, and it's in the lathes that we have, it's supplied by hydraulic pressure. So there's a hydraulic pump, you hear the whining noise of whatever the lathe's turned on. That's that hydraulic pump making that hydraulic pressure. You can actually adjust how much pressure there is. So there's depending on which lathe it is, there's a knob on the side. And you can turn that pressure up or turn it down. You typically would turn it down if you're clamping on something soft that you don't want to damage, and you turn it up when you're expecting high cutting forces. That whiny noise is coming from outside, right? Not from this. Just checking. I was like, it sounds like my hearing aid is at home, but I don't have hearing aids. All right, so that's the clamping force that we're talking about. So let's just call that FC, because I'm not imaginative. What else do we have?
Coefficient of friction.
So friction coefficient.
Hopefully not also FC.
It could be FC, right? But we typically call that mu. So I'll try to make a little mu, a smiley face mu. What else? And so that's the friction coefficient between the vice jaws, the clamping jaws, and the workpiece, right? Yeah.
Spindle speed.
Speed. Is that an RPM?
Yeah. And then total mass of the chuck jaws. And workpiece diameter.
So mass of the jaws and workpiece diameter. And so mass of the jaws, let's call that M. Let's call this D for diameter. All right, so there's a couple different things that we can be worried about when we're figuring out what's the max. The question is, what's the maximum allowable force, right? How much force can we apply in this situation? So there's really a couple different failure modes here. One of them would be that the tool breaks. We don't have enough information to answer that question, so that's not the thing we're worried about. But the tool could explode if we put too much force on it, right? The spindle itself could stall. Right, so if we put too much load, because force equals power times velocity, right? Or no, power equals force times velocity. And so if the force goes up, power consumption goes up. If it's more power than the motor can generate, that doesn't work. But again, we don't know how much power the motor can generate, so that's not the thing we're looking for. So the tool could explode. The lathe could just be overpowered and not be able to do it. The other thing that could happen, which I didn't consider until somebody asked me about this question yesterday, although I didn't consider it when I wrote the problem. I have seen it happen in the lathe, so I should consider it, is we could plastically deform the workpiece. So we could bend it in such a way that it stays bent, right? So we could deflect it, and there's going to be deflection in every situation. Right, and so the deflection is elastic deformation where it bends and it comes back when we're done. We talk about that, but we can plastically deform it. I've seen it happen. You get too much cutting force, the part bends, and then you have this sort of wobbly thing going around, which usually then smacks into the tool holder and then crashes the machine. That could happen. That's not what we're looking for here, though. What we're looking for here is, so imagine the situation where the spindle is spinning and the workpiece is spinning slower than the spindle. So the workpiece has stalled in the spindle. So the friction is trying to keep the workpiece spinning at the same speed as the spindle. If we apply too much load on that workpiece to slow it down, the spindle is going to then spin around the workpiece at some velocity. Right? Or imagine that if the cutting force is mostly pointed in the z-axis, we're pushing that workpiece into the chuck jaws. So it's the same friction coefficient either way. And so the maximum cutting force then couldn't exceed the amount of frictional force we're able to create in our chuck jaw scenario. So we draw the chuck here, right? And so the simple way is just draw this 3-jaw chuck. And we've got a workpiece here. And so we've got this hydraulic pressure clamping it in. And so the frictional force that will keep it, let's just imagine worst case either being trying to spin in the spindle or trying to push it in. It doesn't matter which one it is. So if we're loading it, trying to spin it this way, if we apply an opposite force with our cutting tool that tries to stop it, what's the maximum friction force we can get that stops that rotation? So what is frictional force if you know the friction coefficient? Yeah.
Is it just going to be the clamping force times the friction coefficient?
So you could have the clamping force Fc times mu, and that's the maximum friction force that you could generate in this situation. So if your cutting force exceeds Fc times mu, then it's going to stall in the spindle, unless it explodes the tool or breaks the part or stalls the lathe first. Actually, no, it'll stall in the spindle before it stalls in the lathe, if this is the case. But it's complicated because we have RPM. So what happens to the chuck jaws as we spin the spindle? What direction do they want to go? They continuously want to go tangent to the direction of motion, right? Right, so they're always trying to go this way. So we've got this centripetal acceleration that's pulling the chuck jaws apart, and clamping force that's trying to push them together. So what's the force that's generated by that centripetal acceleration? Right? What do we call it? Centrifugal force? This is like a physics 1 question, right? I could never remember centripetal and centrifugal, but I think I got them right. So if we take the force that's trying to pull the chuck jaws away, and we subtract it from Fc, so what should we call that force? F trying to make it fly apart, Ft, or F trying to make it fly apart. So our real maximum cutting force then is Fc minus Ft, that quantity, times mu, that will equal some F max. And if we have cutting force that exceeds that now, we should probably keep it a little bit under that. It's scary to be right on the edge. But that's, so what you want to do is figure out the force caused by the centripetal acceleration of the mass of the jaws. And I gave you a total mass, so you just have to figure out once, right? So does that make sense? All right, everybody can solve that problem now, right? Got it.
Would the surface area of contact between the chuck jaws and part make any difference?
You would think so. It changes the pressure, right? So, but frictional force is normal force times friction coefficient. So if you had a smaller surface area and the same pressure, the force would go up.
So unless it was rubber and you get more surface area.
Yeah,
That would-
it's
that
just,
wouldn't make
it's intuitively it seems like you gotta have, but it's friction. The force able to generate with friction is normal force times coefficient of friction.
Okay.
So and with something like rubber, that coefficient of friction is kind of flexible.
Yeah.
Right, so it depends on the loading and all the situation, things like that. Once did a project where we actually trying to understand the friction force between the bottom of a tire and asphalt pavement. And which is 1 point something. It's not really that high.
I don't know what that means.
The friction coefficient.
No, like 1 point something.
Yeah, so, well, I mean, have you been in a car where the wheels skidded?
Yeah.
Yeah, so the friction force isn't that high. Anyways.
Okay.
What's next? I knew this would be the one that people had the most trouble with because there's 2 steps. Yeah.
For FT, what will we use?
Right, F trying to fly apart. Okay, FT.
Yeah, what will we use to try and find that, like the centripetal force, like from it spinning?
Yeah, that's all it is.
Okay.
Yeah, so it was R cross omega or something like that, but we have RPM, so there's, Google it. There's a formula. Google centrifugal force or force from centripetal acceleration, or derive it. I would Google it. I trust the engineer's toolbox. Pretty sure Wikipedia even has this one right. What else? In fact, when I created the problem, I Googled that equation to make sure that I had the correct answers. Yeah.
Multiple choice section, the last question, it says measurement is important because, and then it says you get what you inspect, not what you expect. You can measure it, you can improve it. You're good at what you measure, all the above or none of the above. I put all the above, but it says it's wrong.
Say again what the other choices were.
You get what you inspect, not what you expect. If you measure it, you can improve it, and you're good at what you measure, and all of the above or none of the above.
I think all of the above should be the correct answer to that.
Okay.
That's what I thought too, but it's actually it's not that.
Yeah, one of the questions, like in the
So
why the answer is, it says all the above.
Yeah, it says all of the above over here as well, when it tells you that you got it incorrect.
yeah, I'll fix that.
Okay.
And I'll have to go in. I have to fix it individually on everybody the way Canvas works. I can't change. Maybe they updated that. It used to be you couldn't change anything once a student had seen it, and it wouldn't regrade anything. You had to manually go regrade it, which is why it's a pain to have a mistake in a Canvas quiz. I know that like I can't fix a typo in a question once you've seen it.
Okay.
So if he hasn't logged into the test and you have, you will always have the typo, but if I fix it, the next person that logs in won't get the typo. It's a Canvas thing. They call it well, it's in the manual. If you write it in the manual, it's a feature, not a bug. Yeah, so if there's anything like that, there was somebody emailed last night, and the tolerance on the correct answer, so all the math questions that are not supposed to be exactly 0 for the answer have some tolerance of like plus or minus 100 or 1,000 or whatever. And they rounded the answer and the number they put in was just outside the tolerance range. And so they said, hey, I think I should have gotten that problem correct. And I went in and fixed it. So if there's something like that, email, I'll go fix it when I see them email. Yeah.
So I misread the due date for the practice part, so.
It's possible I miscreated the due date, but they're all due the end of the term.
Oh.
You should do the practice before you do the final,
Oh,
because you get unlimited attempts on the practice and it's the same kind of questions.
that's the first part.
Yeah.
Um,
There was a problem with one of the questions where they had pictures in it and you couldn't see the pictures. And so what I did in the practice is I deleted all of those questions from the initial one and then I just created a new one where the pictures worked.
okay, but I'll also get 5 points, you know, that's what I did.
Yeah. It doesn't matter the order you do them. Anything else? Yeah.
Can you go over the one with the turning operation? It says, your original stock diameter is 3.5 inches, your final diameter is 2.5, and it goes to a spindle speed.
Yep,
And it
okay.
asks for the surface feet per minute.
So we've got a turning operation. So it's rotating this way, the feed is this direction. And so we gave you an initial diameter. And I'm gonna call that DO for the original. And we give you a final diameter. And what else?
RPM.
RPM. And so our RPM, and the question was what's surface speed? So S equals question mark. So the surface speed, so you could use one of the formulas that are online. There's a 4 and a 12 and all that stuff. You can just look up the surface speed conversion from RPM to surface speed. Or you could derive it. What I always do is derive it. So it's the circumference, right? So pi times diameter. So we got pi times diameter is the distance per revolution. And so that's inches per rev, inches over revolution. And I want it to be in feet per revolution. So inches to feet is a factor of 12, 12 inches per foot. So I think I divide by 12 now, right? This is correct. That's inches per foot. And so that would give you feet per revolution then, at the end of that for units. And I want feet per, surface feet per minute. What feet per minute? So if I multiply by RPM. And rev per minute. The answer comes out to be feet per minute, right? The problem is I give you 2 diameters, right? So the question is which diameter to use? Mm-hmm. Yes. So if you're doing this because you need to know the answer, not to, so either diameter will work for answering the quiz correctly.
Okay.
I did the average between the two, just because it was halfway in between. And that's sort of the surface speed at this point on the tool, right? If you're doing this because you want to know the answer for some purpose, do the worst case analysis. So it'll be a higher number here. So if a higher surface speed is bad for you, use the higher number. It's going to be a lower number here, and it's actually going to be the surface speed here that determines making that surface. So if you're concerned about the surface speed being too high and not being good for your tool, use the bigger diameter. If you're concerned about how the surface speed is going to impact the finished surface, use the smaller diameter. And again, these are, I mean, often we don't use the pi divided by 12, we just use a factor. And there's formulas you can Google surface speed to or RPM to surface speed conversion, and they're just gonna have a factor there. But, so as long as you're close, and it should work whichever diameter you use. If it gets marked wrong, then tell me and I'll fix it. But I think all those grade correctly.
Can you over number 12 from part 1?
Yeah, but you'll have to read me the question because I don't remember the questions and the numbers.
Okay. So it says, what is the surface speed at the center of
Yep.
the
Sure.
1.25 R5?
Okay, I remember the question now. So we just figured out the formula for surface speed, right? It's pi times diameter over 12 times RPM. Is that the formula we just figured out? I hate to do this on the board because sometimes I just write it wrong or say it wrong. That's why I'm always asking you guys to verify. And your question is, what's the surface speed at the center? What's the diameter at the center?
0.
So we replace that diameter with a 0.
So the whole answer is 0.
The answer is 0.
So the one we were just talking about before this with the
Initial diameter, final diameter?
yeah.
Yeah.
I put in the right number and formula and Ken just marked it wrong.
Yeah, just email me, I'll fix it.
Okay, thank you.
And I'll try to figure out which question it was that you had so that I can fix it in the question pool.
Can you see which
It's probably just the tolerance range, and you're probably just outside the tolerance range, and that's my screw up.
If we flag a question, like the little yellow box, do you see that, or is it just on our end?
What's that?
On Canvas, I'll pull up the quiz so you can see what it looks like for us. We can flag questions.
I've never noticed anybody flag a question,
Okay,
but I'll go look for it, because if you did it, it must show up somewhere.
so this is what we see, and there's these little things. And if you click there, it stays yellow. That's it.
I will ask the people that administer Canvas how to use that information.
Okay.
Yeah, so the problem is there's like 10 questions in a question pool. Each of them has different numbers, and so each one of those has to get entered manually by hand. And so we probably screwed up the tolerance on one of them. I would blame the damn graduate student who did it all, but I can't really blame somebody that did it so I didn't have to. Yeah.
Sorry, you already went over question 4, but I was.
That's all right. I keep talking about it. Which one's question 4?
This was for a given turning operation, what's the maximum allowed cutting force, with backing force is?
Sure. Yeah, so what it comes down to, and so you've got your chuck jaw with the 3 jaws on it. That really doesn't matter how many jaws are on the chuck jaw. You've got your workpiece here. And so we're applying a clamping force in this direction with hydraulic pressure, right? So all of these have this FC pushing in. And so that's trying to hold it together. The thing we're trying to resist is moving the workpiece in the jaws. So if we have too much force, it'll spin in the jaws, or it'll get pushed backwards into the jaws. And so the maximum possible cutting force we could have would be FC times mu, right? But the problem is, as soon as we spin it, then these jaws want to accelerate away from the workpiece. And so we've got a force due to that centripetal acceleration from here. And so what you want to do is find out what is the centrifugal force that's pulling the chuck jaws away. minus F. I think we called it T when we did it the first time. F trying to make the whole thing fly apart. And then multiply that by mu, and that'll be the maximum force that you want to use. And so it'll be dependent on the spindle speed. If you spin the spindle slower, you can have more force. But the spindle speed also dictates the surface speed, and you've got to have your tool in the correct surface speed range. So the other way to get more force would be to turn the handle and get more hydraulic pressure.
And
So, yeah.
Centrifugal force would. Okay.
Physics 1. Who's in Physics 1 now? That means you've already done it, right? Everybody does Physics 1 at the beginning. High school physics 2. Pretty sure. Google it. Pretty sure it's R cross omega. But then you'd have to convert your RPM into angular acceleration. Or velocity, angular velocity. Anybody else? Who's looking at it for the first time now? Nobody? Okay. Could have been. We've still got plenty of time. I'll hang out if you guys have more questions. Or if you want to talk about life. Yes.
Can you go over the uncut chip thickness one?
Sure. And so here's our stylized turning operation, right? So we're spinning this direction. If we look if we put I really can't draw an eyeball, but we put our eyeball right here. So I guess the eyelashes should be on this side. This is eyelashes on both sides, right? And we're looking this direction, straight down that angle, and we draw the picture. We see, here's our tool, here's our workpiece, right? So we got tool, chip, and T1 here is the uncut chip thickness. There's also a T2, that's the chip thickness, and you get the chip thickness by picking the chip up out of the bottom of the machine tool. So you measure that. This uncut chip thickness, if you're looking right along this line here, it's really how far has the tool moved in one revolution. So what's the distance in this direction in one revolution? This direction in one revolution, right? So the distance perpendicular to the edge of the tool in one revolution. So if the tool had a straight edge on it, and you could do that, you could make a tool like this. If the tool looks like this, then and this angle is 0 degrees, then it's the uncut chip thickness T1 equals the feed in inches per revolution, so just inches. As soon as we put an angle here on our tool, it equals the feed times the cosine of the side edge cutting angle. So it's the feed times the cosine of that angle. And you can figure that out with trigonometry, geometry.
What unit should the feed be in when we're using that equation? Because that's the equation I used, but I was much wrong.
So it might have been the angle that you had wrong. Did you use Excel or?
No, I just used my calculator. I used this.
Okay, so just make sure you got radians and degrees correct.
Okay.
Should be inches, I think. So if you think you put in the right answer and you got marked wrong, let me know, I'll check it.
Okay.
Because, yeah, that one's pretty straightforward.
And the angle is the rake angle.
Side edge cutting angle
Side edge cutting angle. Okay.
is this angle. So the rake angle is this tipping here.
Oh, okay. Which is-
And that would be like rotating the tool this way.
Okay. We don't care about that.
Not for this equation, no.
Okay.
The rake angle really impacts the shear angle here. So that rake angle is gonna have a lot of impact on how much force it takes to do the cut. And this uncut chip thickness is really just about how the parameters you use to set the cut up. So it's that side edge cutting angle and the speed, or the feed. I had something exciting yesterday. Actually, 2 days in a row now. I was almost hit by a car making a left-hand turn while I was walking to school. Yesterday, I kind of exaggerate, almost hit. He was sitting it was a Corvette, all the tops open, everything, sitting there, really nice looking car. I was looking at the car. He was sitting at the red light, gonna make a left turn onto Park Ave. So he's coming down Institute. And the walk signal goes. Anybody ever, I walk a lot. So I'm used to my immediate reaction when I hear that little bleep, bleep, bleep to walk is to start walking. When I'm driving and I'm the first car in line, my immediate reaction is to take my foot off the brake. But I have always caught myself. Well, he didn't catch himself. Totally just made the left turn right in front of me. I'm walking in the crosswalk. I don't even think he saw me. It's pretty amazing. As yesterday. This morning, actually almost got hit. Somebody pulling into a driveway, slammed on the brakes. I jumped out of the way. It was exciting. Be careful where you walk. Yeah.
So for that equation, it's supposed to be in radians or degrees on the calculator.
As long as you tell your calculator which one it is. I think I gave you degrees in the problem. Yeah. The question about Excel was if you do cosine in Excel, it always assumes you're telling it radians unless you tell it differently. So if you're using Excel to solve these kind of problems, you got to make sure you sort out your radians and degrees. Let me double check, see if anybody watching live is asking questions. Nobody has posted a question. Okay. I can check over here too. Still nobody has posted a question. But 4 people are watching. Hi, people at home. It's always exciting when you do a live video and people are watching. It's like that dopamine hit. Did they like my post? Do I have a new friend? Oh, there's a comment now. Hello. It worked. Whew, right to the brain. What else is going on? Anybody else? Yeah.
I just had a bit of a weird trouble with calculating the equation, just to make sure I'm not completely dying here. The equation for centrifugal force is mass times angular velocity squared times the radius, right?
Could be.
The results I'm getting are bizarre. I'm sorry, I guess I was over to after class. It's a weird math.
It may be units.
So you convert an RPM to angular velocity, so that's just multiplied by 6, it's 360 over 60. And that's just, isn't that most of like conversion?
All right, so Khan Academy has a video. I like the Khan Academy stuff. Oh, this is a blog post. It's not even a video. Look at that. This one looks pretty good. So we've got radius. We've got this velocity here, that V2 in this picture, or V1, is the surface speed, right? So it's the tangential velocity in this diagram that I have on the screen. Oh, you guys can't see the screen. Talking to the room. The people at home can see the screen. Room. There it is. See if we can scroll down here. Well, this one looks good. ACV. You guys remember this problem, right? So our acceleration. Where's the word problems? What's delta S? This one's not going to have an easy equation. What's next? How about centrifugal force? You guys don't have to stick around if you're done. There you go. So the force is mass omega squared times r, where omega is the angular velocity. But, calculator. Like calculator. Mass, radius, tangential velocity. So that's our surface speed, tangential velocity, or angular velocity. Oh, you can put in RPM. And it calculates force. So give me a mass.
Oh, I think I figured.
You got it?
Yeah, no, it's just the issue with conversion.
Okay, perfect.
Wait, so for,
Yeah, so if you trust the calculator, use it.
wait, that one's over R, you said it was times R.
Because yeah,
I mean, do it.
you use the correct equation. It depends on what direction you're going and what information you have. It's R cross omega. So it's mass times R cross omega. Check out the 2 boxes of fresh chalk after I complained yesterday. See you.
Thank you.
Sure thing.
Thank you.
See ya.
So when we simplify an answer, how many decimals do you want?
But we simplify, I would just upload it however we get.
Use your judgment. It shouldn't.
The autogrid would mark me right if I didn't drop any decimals.
What?
If I had it up to like 6 precision, like it did mark me right.
Okay.
Although
So there are no questions on this test that should matter to any decimal, to a significant degree of precision, except for the answer where the answer is 0. I had no tolerance on that one because that one, it's either 0 or it's not. But if you do think you get it marked wrong because of the rounding, just let me know. I'll fix it.
Okay.
Because there's no need for any of these answers to be that precise.
For the OD turning operation one.
Yeah.
So I'm giving like 1.8. I'm giving 2.0 for the outer diameter.
Use the average.
The average.
That'll be the easiest.
Okay.
I'm not sharing the screen now, right?
so for the centrifugal force, it's can't say I really understand cross products.
Neither do I. That's why I looked up the already figured out equation. So for the force,
I've got
I can share
mv
the
squared
screen.
over r, but I'm mostly confused on v.
So V is the surface speed,
Oh,
the
okay.
tangential velocity.
Okay.
It's the, yeah. So when you get it out of angular velocity into straight line velocity, V is the surface speed, and then just make sure that the units cancel correctly. So if it needs to be feet, then use feet, right?
So it's just m surface speed squared over r.
Yeah.
Okay.
Yeah, that problem, the math part wasn't supposed to be hard. It was just the conceptualizing the problem. So that question is worth twice as much as any of the other questions. And it was really, can you think through the issue because engineering is just a bunch of word problems. It's understanding the question. You can always look up the math.
No, what book to look at?
That's why they want you to have 5 years experience. So you have all the books. Except these days, it's all on Google. Oh, they're dropping like flies online.
What resources are we allowed to use for these now?
Any
Okay.
open books, open notes. I normally say don't talk to each other, but I didn't say that when I posted the assignment, so I guess you can talk to each other too.
Thank you.
See
Have
ya.
a good break.
Thank you for your term. I really enjoyed your class.
Oh, thanks. I have a lot of fun teaching this class, so.
Do you teach anything else?
Yeah, in the spring, I think I'm teaching 3820 in C term. ME3820, it's, computer integrated manufacturing, something like that. I forget the title. Something like computer integrated manufacturing, computer aided manufacturing,
I'll be taking materials processing, is the only thing that comes to mind. anytime.
2820.
Oh, that's fine, okay.
Yeah, no, I've never been asked to teach that one. And occasionally I teach ME4815 or RBE4815.
Cool, well, thank you.
See you. I'm gonna go ahead and end the live stream, but I'll hang out if you have any more questions.